Thank you. Thank you. Welcome back. Today we're going to talk about ice rink subfloor refrigeration failure. You might be wondering, what's this got to do with risk engineering? It has a little bit to do with it. There was a failure involving a HVAC, basically a heating system for an ice rink, and we'll talk about that and how it actually came into play, that the heating system is what was causing the failure. And we'll learn a little bit about how ice rinks work. We'll talk about working with adjusters, and sometimes that they need to keep an open mind, and we'll talk to you a little bit about how this particular adjuster did a couple times. So let's get on into it. First thing, not always is underground piping covered. So you just have to be very careful that you have an endorsement for that, or that your policy actually covers underground piping. And good adjusters always keep an open mind. In this case, the open mind was demonstrated twice in this claim. So to get started, we want to know, how do ice rinks work? Well, if you take water and electricity, you can make ice, right? That's the formula for ice, is basically water and electricity. It needs a little bit of manipulation. That electricity is going to be used to cool it, and we're going to have compressors and heat exchangers and chillers. We're going to get the temperature of some medium down low enough that we can flow it through some pipes and some concrete and freeze some ice. That's what we're planning to do. All right, gives you an idea. Before the concrete is poured, there's a network of cooling pipes and heating pipes. Yes, heating pipes in an ice rink. We'll talk about that. Okay, so what is a subfloor heating system for? It's basically to keep the ground from freezing. So when you build this ice rink and you set it, if it's directly on the ground, eventually the ground will freeze. You see this with LNG tanks. They're either built 3 feet off the ground, or they have a lot of insulation beneath them. Same principle. We can't freeze the ground, or we'll heave it and we'll move that tank. So it keeps the ground from freezing. Now, how does it work? Let's take a look at it. Well, if you look at that top layer up there, you see the floor, and you see the circles represent the cutaway of the tubes that are carrying that very cold refrigerant from our machine shop, from our coolant room. And beneath that, there's a layer of plastic, and then some sand, and then you'll see hard boards of insulation. Below that insulation, there's another system of heating tubes that are laid in the sand, and then there's the soil. And the whole point of this system, of the heating system, is to keep the soil warm, but not to warm up the floor above it. So you've got that insulation and sand in between. So you got refrigeration going on at the surface, you've got heating going on down below the insulation to keep the ground from freezing and heaving. All right. Now, what were the indications that this system was leaking? How would they have detected that they had a problem with that heating system? Well, as the floor heaves, those walls, the barriers around the ice rink will tilt, and they'll move, and they'll warp, and they'll get out of position. And you'll have maintenance crews out there trying to tighten them up and drilling extra holes to try and rebolt them to the floor. All this is going on while the floor is just continuously, slowly rising in various places. The ice itself could turn the color of the refrigerant, and it'll be below the floor surface, so you'll be skating on green ice. And it doesn't stay hard very long when you get refrigerant mixed into the ice. Ethylene glycol doesn't freeze very well. And then the other thing is if you're having to add your refrigerant very often, or more often than normal, that's an indication that you've got a leak. It would be great to have a system that monitored the reservoir, the return reservoir, and whenever the level went down, you could go start looking for a leak. All right. How did we find this leak? We knew we had it. We knew the walls were buckling and bending. We knew the floor was turning green. We were adding the refrigerant. Now what? How do we find the actual leak in the floor? Well, we brought in a special team that had air. They'd use air compressors to pressurize that HVAC system, or that heating system that was warming the ground, and listen for air leaks underground with ultrasonic detection equipment. And that's what they did. And they found one spot that the signal was very clear. So to be careful, they dug a large hole. It was a 10 foot by 10 foot concrete, hole cut into the concrete. We talked to the adjuster and said, look, this is what we're going to do. He said, when you get that hole open before you go any further, I want to come see what you see. So we didn't touch the insulation or the sand or anything after we got that big slab of concrete up and out. The adjuster got there, and when we pulled back the plastic barrier, we could see that there was a depression in that plastic. Okay, so the concrete's gone. We're looking at the floor. There's plastic over that sand, and the sand is kind of washed away in one certain area. Well, everybody points to that and says that's where the leak is. So we carefully go down there and we cut open the plastic, and we look and we find in the sand a plastic T fitting part of that heating system, and it's broken and it's snapped off. So we get a saw, we cut the other two legs of that T off, and we start to look at it very carefully. The adjuster's looking at it, and before I can even nudge him in the direction of a brittle fracture, he recognized right away that it was not a fatigue crack, that it was definitely a brittle fracture. It happened at once. It didn't happen over time. So he was certain that this was a failure, but he wasn't quite sure that it was the one that caused the floor to fail. So what he said was that broken fitting may have not been the first pipe to break. It may have broken because of wear and tear caused by it may have broken because of another pipe break that was caused by wear and tear. So that's a stretch. He's just throwing out scenarios when we've cut the floor open, we've found the leak, it's brittle, he doesn't need to go down any farther, but he throws that out there. He says, this may not be the only leak. You're going to have to dig up this entire floor. I want to inspect all of this piping to see if any of the rest of it's leaking. Well, that was a tough one to swallow. Fortunately, it was lunchtime. It was going to cost a few $1 million to dig up that entire floor. And the owners of this facility didn't have it, and if this insurance didn't cover it, they were going out of business. So that's what we were faced with, was closing the doors on the hockey rink, on the ice rink, or figuring out a reason that this claim was covered. So we go back, and we got the adjuster to change his mind, believe it or not. And after lunch, I had a little time to think this through, but I asked him a question. I said, why was there a depression in the plastic? And he got to thinking about it, and he said, well, the refrigerant had to leak out and wash the sand away. And I said, well, if the refrigerant leaked out when that pipe broke, it must have been full. And it wasn't a consequential break, it was the first break. Otherwise, the piping would not have been full. And he looked at me, and the light bulb went off, and he basically said, this claim's paid. Just like that. That's all it took. Once he had the connection, the logical connection, that there were no other breaks under that floor that we were going to find that led to this particular spot breaking due to a consequence of something to do with the first break. He saw it. He knew that, okay, this is the only break. It was brittle. The claim's paid, and it saved the ice rink. It saved the team, and they got to continue holding semi-pro hockey games there. So with that, thanks for coming along. Hopefully this one satisfies some of your curiosity about ice rinks, a little bit about working with adjusters and claims, and keeps you on the path of being a good risk engineer. Come back for the next one, and don't forget to like, share, and subscribe.